Welcome to class number 7, session number 4. This session will focus on carbon nanotubes as chemical sensors in the gas phase. Carbon nanotube-based electrical sensors for gas applications are based on similar transduction mechanism to those in the liquid phase, such as those we have described in the previous session. Here is a representative example for sensing mechanism of bare carbon nanotube-based electrical sensor. Bare carbon nanotubes interact non-selectively with numerous gases, typically with large binding energies, thus resulting in long gas deposition time constants. Therefore, sensitivity, selectivity, and reversibility improvements for carbon nanotubes can be achieved by creating defects along the sidewalls of the carbon nanotubes and can introduced by various chemical and physical treatments as well. For example, acid oxidation increases the surface area of carbon nanotubes, creates sidewall defects, and simultaneously introduces functional groups at the defects on the nanotube surface. Another example is the acid treatment can be also combined with plasma treatment for a two-step functionalization, and also plasma treatment can be implemented as a standalone process to create oxygenated groups. Besides enhancing the organic and inorganic gas responses, carbon nanotube oxidation also promotes its response to polar vapors, including water vapor, bringing a significant problem of water interference. The mechanism of adsorption of the polar molecules onto the oxidized surface of carbon nanotubes is the alternation of the electronic properties of the semiconductor carbon nanotube surface by charge transfer induced by the adsorption of polar organic molecules. The adsorption of such molecules is due to the polar nature of the surface, as well as that of the solvent molecule, as shown in the figure. The carbon nanotube surface contains polar functional groups which can adsorb solvent molecules, and here is the source of the problem or the interference. Functionalization reactions of single-wall carbon nanotubes and multi-wall carbon nanotubes can be broadly categorized as covalent and non-covalent. Covalent functionalization reactions include direct attachment of functional groups to the graphene surface, and also attachment of the functional groups throughout imidation and other routes of modification to the nanotube bond carboxylic acid groups at the defect sites. Non-covalent functionalization approaches are more diverse and include functionalization with organic molecules of different chain length, chain branchings, aromatic configurations, and functional groups that include biomolecules and synthetic dielectric polymers, conducting polymers, metal particles, and more. An alternative approach to the use of sensors that are based on individual carbon nanotubes is the application of random network of single-wall carbon nanotubes. Using random network of single nanotubes circumvent the requirement of position and structural control because of the devices display the averaged property of the carbon nanotubes. An additional feature of the single-wall carbon nanotube networks is that they can be processed into devices of arbitrary size using conventional microfabrication technology. In the case presented on the screen, interconnected single-wall carbon nanotube networks are exploited to recognize the identities of different chemical gases by strength of their particular surface adsorptive and desorptive responses to various types of chemical vapors. The physical responses on the surface of the single-wall carbon nanotubes cause superficial changes in the electric change and the electric charge that can be converted into electronic signals for identification. Actually, in this case, nitrogen dioxide and ammonia vapors are tested at ppm levels at room temperature with a self-made gas sensing device. This exposure process shows responses to concentrations as low as 10 ppm for nitrogen dioxide and 24 ppm for ammonia. Adding functional organic groups on top of the carbon nanotube random network is an excellent way to enhance the sensitivity of these carbon nanotube-based devices. In the example presented on the screen, 10 chemoresistors were coated with a random network of carbon nanotubes and functionalized with a wide variety of non-polymeric organic materials. The bare and the functionalized devices in this case were tested as sensors array for detection of diverse volatile organic compounds and water vapor. The right figure illustrates the scores plot of the PCA model of the sensor array response for various volatile organic compounds at different levels of concentrations. As could be seen in the figure, each tested volatile organic compound produces a unique response pattern that have different direction in the principal component space. In this context, please note that the pattern height is proportional to the Vogt concentration in the vapor phase. Altogether, these results show the ability of the functionalized random network carbon nanotube devices to separate not only Vogts, but also between their constituent concentrations. As seen in the current slide, employing polycyclic aromatic hydrocarbons with various aromatic coronas and functional substituents allows reliable discrimination between polar and nonpolar groups and also between different components of each of these groups. The right figure presents an image plot of the response values calculated from the pristine or bare single-wall carbon nanotubes and the carbon nanotubes that are modified with the polycyclic aromatic hydrocarbons upon exposure to various concentrations and in a background humidity. In most cases, good discrimination between the volatile organic compounds and the water signals is obtained. A cross-reactive array that is based on the polycyclic aromatic hydrocarbon and the carbon nanotube sensors are provided, and DFA and PLS recognition methods exhibit discrimination between the various Vogts or the volatile organic compounds in mixtures with either 5% relative humidity or 80% relative humidity. Using appropriate combinations of polycyclic aromatic hydrocarbons and single-wall carbon nanotube sensors, the sensitivity and accuracy of the cross-reactive device arrays is tailored according to the detection or the application of interest. Combining the sensors with the PLS algorithm, such as presented in this study, allows prediction of the Vogt concentration in various constant humidity levels. Right now, we will move to photosensors that are based on carbon nanotubes. Tunable photosensor field effect transistor devices were fabricated to sense a fluorescent ruthenium complex molecule. In this case, when the light was on, namely at wavelength of around 280 nanometer, the transfer curve of the field effect transistor device shifts towards a negative gate voltage by around 1.6 volt, and its sheet resistance increases quickly, indicating a charge transfer process from the receptor to the single-wall carbon nanotube. On contrast, the transfer curve of the device is the presence of the ruthenium complex molecule shifts towards a positive gate voltage by about 1.9 volt. And its sheet resistance decreases slowly when the light is on. In this case, the wavelength is 490 nanometers. And by that, it shows a charge transfer process from the single-wall carbon nanotube-based hybrids to the ruthenium complex molecule. Because these photoresponse processes are recovered following the removal of the light, the presence of photoresensor exhibits a promising application in the area of tunable light detection. Altogether, these results raise the prospect of promising applications in the area of tunable light detection, as in the artificial eyes and PVDs. Microcantilevers have been used to measure small masses. And around a decade ago, it became clear that if these cantilevers could be made small enough, their sensitivity would approach the mass of a single proton. Indeed, a race to the bottom ensured with demonstrations of ever better level of sensitivity from femtogram throughout attogram and zeptogram to sub-zeptogram. Researchers now report that they have passed another milestone in this race by demonstrating yoctogram sensitivity with a nanotube-based mass sensor. Please note that a yoctogram is 10 to the power of minus 24 gram. This is exciting because the ability to distinguish masses that differ by one proton mass, which is more or less 1.67 yoctogram, could lead to mass spectrometers based on nanotubes or other nanomechanical resonators that would have several advantages over the existing mass spectrometers. Another reason for this excitation is that the surface science techniques tend either to observe molecules that have been frozen into place by the use of low temperature or to treat diffusing atoms in assembles. The sensitivity offered by the nanomechanical-based mass sensors could be used to study the adsorption, desorption, and diffusion of individual atoms and molecules on surfaces. The presented figure on the screen illustrates how atoms often move around constantly after landing on a surface. The upper schematics demonstrates that the mass sensor contains a single carbon nanotube suspended over a trench in a silicon or silicon dioxide substrate and attached to metal electrodes at both ends. This nanotube vibrates with a characteristic resonance frequency, which changes as atoms or molecules, shown here in red, land on and migrate along the nanotube. The lower schematics shows the resonance frequency versus time before and after the nanotube is annealed by passing an electric current throughout it. Before annealing, the diffusion of atoms or molecules along the nanotube leads to frequency fluctuations that limit the performance of the device as a mass sensor. These fluctuations are dramatically reduced by annealing, which allows very small changes in frequency to be detectable. The thickness of the red line can be thought of as roughly equivalent to the frequency change associated with one proton mass. These devices also allow the interplay between the absorption, desorption, and diffusion of single atoms or molecules to be studied with these type of sensors. A modified system of ultra-sensitive mass sensors that is based on carbon nanotubes can be used for measurements and analysis of the kinetics and fluctuations of physisorped atoms such as xenon. The measured adsorption spectrum and frequency noise, combined with analytic modeling of surface diffusion and adsorption-desorption processes, suggest that diffusion dominates the observed excess noise in the presented example. This study also reveals new power laws of frequency noise induced by diffusion, which could be important in other low-dimensional nanoscale systems. We reach now the end of class number 7, session number 4. Thank you.